That's where we stopped 2 days ago. We discussed with you the second large category of subspaces. I call them span subspaces. This is a general description of those subspaces. They all, in short, you can describe them as a collection of all linear combinations of a fixed set of vectors. So we start with a fixed set of vectors S like this. We take all possible linear combinations of these vectors, we collect them together, and it turns out to be a subspace. As a matter of fact, this category is even larger than the first category we discussed 2 days ago. The first category was, if you remember the name I attached to that category, it was the name was orthogonal complement subspaces. I say this one is a larger one because if you think about that, if you make an effort and think about that, the orthogonal subspace category, it was entirely within this kind of subspaces. I mean, from the start, when I introduced orthogonal complement subspace, it lived within this particular choice of a vector space. There is no any analog of orthogonal complement subspace if you take any other example, any other fundamental example of a vector space. Whereas span subspace, it's a construct you in principle can realize in any of the existing fundamental examples of vector spaces. Okay? Look at this, because the span construct starts with any vector space, not specifically this vector space. However, most of the time you will look at the span subspace within the context of this particular vector space and tuples of numbers, rational numbers, real numbers, or complex numbers, depending on your choice for f. And that's my next slide is about. I'll show you that actually span subspace in the context of this particular vector space, not a general vector space, but in the context of n tuples subspace, it takes even more familiar form for you, and that's the content of my next slide. Look at this. This is an example from the yellow book. It's a tutorial question 22. Oops. That's what the question says. It introduces the following set of vectors. Let's just look carefully for the set of vectors like this. It's all two-dimensional vectors, two couples of numbers, real numbers, such that every such couple, every such vector results as a product of matrix A and some vector in R3, some triple of numbers. Question 22 specifies the matrix A quite particularly. That's what it suggests for the choice of a matrix A. If you're comfortable with the matrix multiplication, and I expect you be comfortable with matrix multiplication, that's the content of the first semester, then everything looks nice and compatible. This is a vector which is a column 3 by 1, 3 rows, 1 column. You multiply by the matrix 2 by 3, you end up with the vector here of the size 2, like this. So that's a set in equation 22. The question itself asks to confirm that this set is a subspace. What I will do, you can of course do it directly by the subspace theorem, the one we discussed with you 2 days ago, the one which requires to verify 3 criteria. You can, but what I will do now instead, I will link this set S to the span subspace, the one which I just showed you at the beginning. And if I do that, I can rely on this general result that every span subspace is in fact subspace. And that will be a linkage which will show you that all of these examples, all examples of this type, can be fit into the general scheme of span subspace. Look at this. So here's my interpretation of this set once again. So for the vector B to be in a set, it must be reproducible through this relation. So for the vector B to be in a set, there must be a triple of numbers, x1, x2, x3, in R3. Remember my convention. If I label a vector with letter x, it means it's conventional to label the entries of that vector with the same letter, indexed appropriately. So for my vector to be in S, there must be, the symbol reads exist, there must be a triple such that the triple works like this. Again, if you're comfortable with the matrix multiplication, this right-hand side, if you just do this matrix multiplication with this matrix A and this column vector X, that's what it's going to be. The first component here is a dot product of the first row in here and the column. The second component here is again a dot product of the second row and the first column here. This is how we do matrix multiplication. If you're not comfortable with that, you need to revisit this subject from the first semester. So this is the result. I mean, if my vector B is assumed to be in S, which is described like that, then there must be a vector which makes B look like this. If I now do an extra modification of this result, because here we're looking at the vector with two components. It's the first component of my vector, this is the second component. If I split this into the sum like this, look at this. If I combine all of the x1 coefficients into one vector, all of the x2 coefficients into another vector, all of the x3 coefficients into a third vector, is my combination. So x1 comes with the coefficients 2 and 4, right in here. x2 comes with the coefficients -3 and 5, right in here. x3 comes with the coefficients 1 and -3, right in here. If I do these modifications, you can see your span, because this is something which I called on my previous slide linear combination. And it looks like that my B, which originally was assumed to be in S, it looks like that this B is representable as a linear combination of these three given vectors. So I can say now that my B belongs to the span of these three vectors. Because to be in a span, it means that the vector is the linear combination of the set underneath the span. So this just goes to show you that many examples in the yellow book which are framed in these terms, which are framed in terms of matrices, they are special cases of the span subspace example. And now I can say that this set S is indeed a subspace because every span is a subspace. In fact, I can make a generalization. That's the one which I'm going to refer to often. I can now say, by looking at this example, the way we treated this example, we can make a general statement now. Excuse me, gentleman in white t-shirt, you. Tell me please, what's your name? Tim. It's a fourth person I know. Tim, tell me please, why this thing is a subspace again?
So it satisfies three criteria.
Did I show that? No. But why do you think it does?
Because if you try three criteria, it will satisfy.
Is that the way I explained it? I think we just discovered a better way to do that. No? Oh yes. Well, you're right, in fact. You can do it directly. You can check these three criteria directly. But in my opinion, a more effective way will be just making this one look like a more general example of a subspace, a span subspace. And that's exactly what we just discovered. Like actually, all of these examples, rather than doing them directly, you can link them to the second category of the subspaces, which I call span subspaces. It doesn't mean you don't have to do it direct. Once or a few times you will need to do it directly to convince us that you can do it. But linking this to the span subspace, it's a very professional way of doing it, actually. Anyway, so now I can make it, thank you very much. Now I can make a general observation, which is, that's the name I'm going to use to refer to this thing. It's called span in fn lemma. And that's the general observation which is inspired by the way we did this example just now. That's how I can generalize the method we just discovered with you. I can say that whenever you look at a span of some vectors, in this case m different vectors, you can equally identify the subspace with a subspace which is structured like this. It's all of the b vectors representable as the product ax, where this A matrix is linked to the A, little a vectors like this. The A matrix is in fact the one which is composed of these vectors as columns. And that's what I was trying to say here. If you take these vectors as columns, you see what happened here? Every column here went into a vector, and vice versa. If you take these vectors and you put them into the matrix as columns, you will end up with A, which is needed to find this alternative representation for a span. That will happen very often in the yellow book. You will be given, there will be a question asking whether a particular vector belongs to a span, and effective way of doing it will be through this span lemma. I'll show you one example. Any questions, please? I'll show you one example where exactly where exactly this works. It's a slide which I call testing vectors in a span subspace. So here's the example. We have, yeah, it is a tutorial question. It's a question 34. The question gives us 4 vectors. Here they are, all of them, A, V1, V2, and V3. 4 vectors, three-dimensional vectors, so 12 numbers altogether. The question goes to ask whether A belongs to the span of these 3. This is the place where you're going to go the opposite way. I mean, on my previous slide, I went from the matrix representation to a span. This time, I'll go the other way around. From the span, I will go to the matrix representation. So if I use my span in fn lemma from the slide before, I can say that for the vector A to be in a subspace like this, you need to make sure that there is a vector in X3 such that your A is representable through matrix multiplication of this type, where A is the one which is composed of these V's as columns. This is the idea we just discovered on the slide before. Rather than testing directly in span, I build a matrix which composed out of V1, V2, and V3 as columns, and see if my A representable like that. So here's my A matrix. I just copied my V's, V1, V2, and V3 here. 1, 2, and 3. And now I need to answer the question whether my A, this first A in here, can be given such representation through a particular choice of X vector. If you forget about all of this wrapping around it, the span or belong to a span, this kind of tasks, by now you have to be very, very proficient with, because basically it's a solving of system of linear equations, because that's your, well, it is on the right-hand side as a matter of fact, but canonically that will be the left-hand side. X will be your unknown or unknowns, 3 of them, x1, x2, x3, and you solve your system, you solve for this unknown, so that you end up with the right-hand side like this. By now, you know how to do it in a very robust, universal way. It's a method which we call Gaussian elimination method. So if I solve something like this, I need to extract augmented matrix of this system. Here it is. Now it is like the left-hand side properly on the left-hand side, right-hand side is properly on the right-hand side. Left-hand side is exactly my A matrix from my system of linear equations. Right-hand side is exactly my right-hand side, this vector we're trying to realize through this product. And when we solve this, we know how to do that. We need to take this augmented matrix to the row echelon form and see if the criteria of solvability are applicable or not. I'm not going to take this to the, I'm not going to show you the details of taking this to the row echelon form. So I hope you can trust me. If I take this matrix to the row echelon form, that's the kind of result you will come up with. In fact, I here recorded all of the elementary row operations which I needed to achieve this row echelon form. You can double check if you wish. So first you need to swap row 1 and row 2, then you have to do this transformation, this and this. Yeah. These 4 transformations, in fact, they are hidden by these dots. By now I think the first semester you'll be doing this quite a lot. I think by now you're quite bored with the row echelon forms. That's why I'm taking these computational details away. But if you want to double check me, you can always recover this. That's the steps which are taken to take this matrix to this row echelon form. By looking at this row echelon form, we can spot 3 pivots. And when the row echelon form has 3 pivots, that's the sign that the system has a solution. In fact, it's a sign that the system has a unique solution. And so the answer to my question will be yes. Yes, the vector A belongs to this span, because this existence required for this to work, it is established through existence of these 3 pivots. So after doing a few such examples, you will realize that on a technical side, dealing with span is not so new to you, provided you had enough experience with the row echelon forms and systems of linear equations in the first semester. After all, it will all boil down to looking at the systems of linear equations and the associated row echelon forms of those systems of linear equations. Okay, and the why this is so, it was the content of this span in a fan lemma, which linked span to a system of linear equations like this, where A is a matrix built from V vectors as columns. This is the step which is done by my observation we've done today. Nice. Okay, any questions? All right, if you don't have any questions, this slide actually gives me the opportunity to introduce another piece of a terminology which will broaden our language a little bit, and which appears in the yellow book quite often. Here it is. A set of vectors from 1 to M for Mary, within a vector space. V is a vector space here, any vector space, not necessarily Rn or any vector space. Such a set will be called spanning. Such a set will be called spanning if and only if the vector space can be recovered as a span of the set S. Okay, that's just a piece of a terminology which you will see often. From the structural point of view, it's quite a significant piece of a terminology. In fact, because if you think about this carefully, you will realize that the vector space, which is like an infinite object, which has infinitely many components within it, can be linked to a finite set of vectors all together to the span. For instance, if you take this set, this particular set, this set of these three vectors up here, v1, v2, v3, and if you ask whether this set is spanning for, so if you take this set, if you take this set, this particular set, and if you ask, this is a set, of course, within the scope of R3, so it's a kind of setting of this type. And if you ask yourself whether this set is spanning, is it? The definition right in front of you here in the corner. The set is spanning when every vector in V can be recovered as a linear combination of these given three. So is it spanning or not? Whereas I know 4 people in the class now. There was Richard, there was Carrie, there was Matthew from last time, and now Tim. Where is Matthew, please? Do we have Matthew in class? Go ahead. Is it spanning? Yes. Why? Any evidence? It says so. It's a question mark here. What we need to do to confirm, you're right actually. Well, it's not a hard guess. It's 50-50 either it's spinning or not spinning, right? You can flip a coin and just make it 50% of the chances you'll hit the right answer, except for the people who doesn't like probability. Yeah, right. So it is spinning. That's right. How would you convince everyone else that it is spinning? What we need to do to see that it is a spanning? What we need to do is this. We need to take any other choice here. I mean, we need to see that whichever choice of A I do here, and I can make any choice here, any vector from R3 I can put here, no matter which choice I make, the whole argument which I just repeated for this particular A still stands. But if you analyze this argument, you will realize that the whole argument spins about one single place here, the 3 pivots. And even if you change your A on the right-hand side, no matter which way you change this A, these 3 pivots, they still be there. Something will be different on the right-hand side, but 3 pivots here, they still be there. And that's the main evidence which tells you that these 3 vectors, in fact, they are together, they make a spanning set. Because any vector on the right-hand side, for any vector on the right-hand side, you can find this x in here. And you can do that only because when you do row echelon form, for these 3 vectors, on the principal side of your augmented matrix, these 3, they give you a pivot. That's the way you will argue on many occasions that the set is spanning. Any questions? Here's another example of testing that something is spanning. It's another question from the book. It's a question 41. It's another question from the book. It's a question 41. That's the question. So it goes to ask whether the set of these 3, well, they are polynomials, but we think of them as vectors now because if you remember, we made this object one of our canonical examples of vector spaces. It's a collection of all polynomials of degree 2 or less. So the question goes to ask whether the set of these 3 is spanning for this vector space. All you need to do, you need to carefully follow what the definition says. Look at this. Being a spanning, it means that if I take a span of this S, I can recover the whole vector space. Now I'm going to expand what that means. It means that whenever I take a vector from my whole vector space, and I'm free to choose any vector. This is a symbol which says any. Whenever I choose a vector from my vector space, I can convince you that there will be always a choice for free numbers, lambda 1, lambda 2, lambda 3, such that my Q is recoverable as a linear combination of the fixed free. This one I call P1, this one I call P2, this one I call P3. That's the whole idea of being a spanning set. You can recover any element in your vector space as a linear combination of this fixed finite set. In this case, P1, P2, P3. If I make my expansion even further now, because right now it's all vector language, it doesn't really involve the nature of the objects underneath. If I now involve the objects underneath, here it is. So left-hand side, well, actually, it's the right-hand side, but it turns out I'm going to put it on the left-hand side now. Here's the left-hand side, my coefficient. I need to convince everyone that there is such a coefficient. Then the P1, that's the P1 from here. My second coefficient, and the P2 from here. And the last one, and the P3 from here. This is just the expansion for this side of the equation. For Q, I'll choose because it's a polynomial of degree 2 or less. I'll give Q a structure. So that's the structure of my Q. And now my original question whether this set is spanning comes down to the question whether for any choice of coefficients on the right hand side here, I can find lambda 1, lambda 2, lambda 3, which make this identity work. Now this idea of being spanning is fully opened and fully encoded or decoded in the language of the particular, in the nature of the particular vector space of polynomials of degree 2 or less. Listen to this again. So what I need to answer is this. Whenever I have any set of free numbers A0, A1, A2, I can always find coefficients lambda 1, lambda 2, lambda 3, which makes this identity work. After you've done this, you will realize it's again some sort of system of linear equation analysis, right? Because if two polynomials are equal to each other, this is as good as I need more friends in this class, right? If two polynomials are equal to each other, this is as good as the coefficients next to the corresponding powers of x equal to each other. And that's what I'm about to do. I'm going to take the coefficient next to x squared on the left-hand side, which is double lambda 3 and negative lambda 2, and equate it to coefficient next to x squared on the right-hand side, which is A0. Now, coefficient next to x, which is lambda 1 plus lambda 3, and the corresponding coefficient here is just A1. And the free one is lambda 1, lambda 2, and A2 on this side. So again, if you restate my intentions now in terms of the just A0, A1, A2, and lambda 1, lambda 2, lambda 3, here's the statement, or here's the restatement. For any right-hand side, I need to be able to find the solutions which works for this system. That's what you're going to do very often. You're going to start with a very condensed statement. A set is a spanning for a vector space, and then you're going to unravel it down to some sort of system of linear equations through the nature of the space, through the explanations of what it means to be spanning. And eventually you will end up with a system of linear equations, and you will do the analysis of that system of linear equations. Again, the analysis we do through row echelon forms. So for this system, that's the augmented matrix. right? I just copied all of the coefficients from the left-hand side on the left-hand side of my matrix. My right-hand side, it comes with just symbols, A0, A1, A2. You take this to the row echelon form. Yes, and I do take it to the row echelon form. Again, I don't really expose the actual computational details. I'm sure you can do it on your own. When you take this to the row echelon form, that's the resulting row echelon form. You see, I didn't bother actually to do the arithmetic on the right-hand side because it's not really relevant in the current context. That's why I just replaced the right-hand side with some other symbols. There will be some other symbols there. With some effort, you can recover the exact relations between this A0 dash, A1 dash, A2 dash, and the original A0, A1, A2. But for the current question, it is irrelevant. What's relevant is the 3 pivots on the right-hand side. This is relevant. Having these 3 pivots, it's the this is a sign that yes, S is indeed spanning set for the P2R. For this P2R. Any questions? Well, that's basically all of the techniques you need to know when you deal with spans. I also showed you the techniques. How to deal with the first category of the subspaces, the orthogonal complement subspaces. I showed you how to combine them together through intersection. I have only one slide left for today's discussion. It's about actually what you do when you need to show that something is not a subspace. There are a few questions in the yellow book where you need to do that. I showed you one example 2 days ago. It was a relatively simple example. There was an example of a non-subspace. We saw that through the fact that the first criterion was not satisfied in that example. 0 didn't belong to the set. I'm not sure if you followed my uploads on Moodle. On Moodle, I put together a few other examples here in this section. I made the upload of the lecture 7, I think it was this morning actually. Here, under this section supplementary material, I showed you, I put here these examples of non-subspaces. That's the more examples or more techniques which you need to do when you see something is not, when you need to convince someone that the particular set is not a subspace. I'll do one example today in class. That's the example which is not in this set. And I do this because last time one of you came to me and asked what happens if you take a union. Because last time we discovered if you have 2 subspaces, if you take the intersection of them, you will end up with a subspace again. But I didn't say what happens if you take union rather than intersection. And one of you came to me and said, well, what happens? And the answer is no. In general, when you take a union of 2 subspaces, it doesn't mean you will end up with a subspace. And that's the thing which I'm going to discuss with you. Yeah. So here's the setting. It actually works in the scope of every vector space. So if I have a vector space, I have 2 subspaces. In fact, this is a question 31. That's how I realized. Question 31 in the yellow book is exactly about this. It goes to ask whether a union of 2 subspaces is a subspace. The answer is no. So if I build a new set, which is a union of 2 subspaces, the claim which I make is that this is not necessarily not a vector subspace in general. We know, on the other hand, if you take rather than union, if you take intersection, this one we know it is a subspace. That's something we discovered with you 2 days ago, and we used it actually. But if you take union, it is not a subspace. Union, as you know, that's the explanation what the union is. Union of two sets, that's the collection of elements which belong either to one or the other. Unlike the intersection, where it's a collection of those vectors where they belong both to one and the other. So in fact, the difference between the union and intersection is just in one word. It's either or and. If it's and here, if you replace or for and here, it will be intersection rather than the union. Right, so if you show something not a subspace, especially in such a general context, you need to provide a particular numerical counterexample. Here's the counterexample, which is very nice. Which shows you that if you take a union of two subspaces, it is not necessarily a subspace. My first subspace, W1, will be span of this vector, 1, 0. You have a bit of an understanding what the span is. Now I can use these notations to make my exposition shorter. So my V space, it's the R2. My W1 is like this. My W2 is like this. These two, we know they are subspaces because every span is a subspace. So these are the subspace. What I claim is, if you take the union of these two, like this, I can kill this, I can kill this. If I take a union of these two, the union is no longer a subspace. And I will claim this by showing that one of the criteria in the subspace theorem, they are not satisfied. Here we go, look at this. If I take the x vector, 1, 0, it is in the W1, because it's in a span of 1, 0, and by implication it is in a W, because W is a union. It's the vectors which either belong W1 or W2. If I take y vector 0, 1, it is in W2, and by implication it is in W. On the other hand, if I add them, the result will be 1, 1. And the vector 1, 1 is not in W1 because you cannot possibly reproduce this vector as a span of 1, 0. Because span of 1, 0, it's all possible linear combinations of the vector 1, 0. Linear combinations of one vector, just all possible scalings of that vector. No matter how hard you try to scale this vector, you will never end up with 1 in the second component. That's why this is not in W1. Similarly, the same sum is not in W2 because, again, no matter how hard you scale this, you will never get 1 in the first component. And here's my contradiction. I took two vectors in W, particular numerical examples of vectors. You have to, when you make a counterexample, it's your job to make a particular numerical counterexample. I took two vectors from W such that when I add them, the result is not in W, because it's neither in W1 nor in W2. That's why for this set, the third requirement, the third criterion of the subspace theorem fails. And that's why this is not a subspace. So interestingly enough, the other two criteria on the subspace theorem, the first one about the zero vector, and the second one about the scaling, I think it was the other way. The way I indexed my criteria, now I realized, the second one was the closedness with respect to addition. The third one was closedness with respect to scaling, scaling. So in fact, the second one failed here. The addition fails here. The other two criteria, zero and scaling criteria, they work perfectly for this example. Zero is in this set because it's in this set and in this set. And if you scale an element of this set, you will end up with the element in this set. In fact, I encourage you to check that. So this is one of these rare examples, where exactly addition criterion, closedness with respect to addition criterion fails. In many other examples, you just fail either 0 or scaling, whereas in this case, the only way to fail it is the addition.